We have at least asserted that the solution to this equation has the general form x equals a cosine of omega t plus phi, and I've actually called this phi sub 0 for no particularly good reason, but since I've called it that, let's go ahead and call it that. Now, we've pretty much shown that this is true, but there's some blanks that would need to be filled in. We don't really need that. We just need to understand that this is a general solution of this equation. It has two constants. It has a, and it has this phase constant, which I've called here phi sub 0. This is to be expected when we have a second order equation. If we do two integrals to get x, whether we actually do two integrals or not, we're going to expect to get two constants. So we get the two constants, a and phi sub 0, to the second order equation, mx double prime equals negative kx. And this omega, I don't know that we've mentioned this omega, but this omega is just the square root of k over m that we saw before. So it's just a shorter way of writing the square root of k over m that we saw in the original equation. Now, if x is 0.5 meters when t equals 0, that means, of course, we write that as x of 0 equals 0.5, and I'll go ahead and keep the meter here. Now, x of 0 equals a times the cosine of omega times 0 plus phi naught. And omega times 0 is just 0, so this is just a times the cosine of phi naught. And this equals 0.5 meters because x of 0 is 0.5 meters. So we have the equation a cosine of phi sub 0 equals 0.5 meters. Now, we've still got two constants. We've got a and we've got phi sub 0. So we don't yet know what either of these is, and with just one condition, if the only condition we have to satisfy is that x equals 0.5 meters when t equals 0, we could choose any value of a and find the phi sub 0, or we could choose any value of phi sub 0 and find a value of a that makes this true. But we don't have any unique pair of numbers for a and phi sub 0 that'll make this equation valid.